thinking of some technology that could potentially have a huge impact on how everything in machine learning happens.
Mm-hmm.
Something that is around today, though very much in its infancy, is quantum machine learning.
Mm-hmm. Mm-hmm.
And you have a fair bit of exposure to this because prior to Cohere, you were at Zapata Computing,
Yep.
where you were a quantum AI research scientist.
Yes.
So tell us about quantum AI. And I know that you actually already listened to Amira Abbas's episode.
Yeah.
So Amira Abbas, incredible communicator on quantum machine learning. We had her in
Yeah.
episode number 721. I was pursuing her for literally years to get her on the show. And so
Uh-huh.
that's a great, that whole episode is an introduction to quantum machine learning. But let's do a mini one here, especially because you might have different perspectives from her. So Amira, it was interesting, her overall sentiment was that at this time, with the number of qubits that quantum computers today can handle and the number of qubits that they're going to be able to handle over the next several years, she didn't think that there were practical, real world machine learning applications that we could handle with quantum computing. But I'd love to hear your thoughts.
Yeah, no, it's great you had Amir. Amir is really a top scientist in the field and a great communicator as well, which is rare to find. So I've asked her a lot of questions in the past few years, and she's very very knowledgeable. Yeah, I think I agree with that. Definitely, right now you can't do very much. So our research was based on like two things basically. Question one was, is there anything we can do that is meaningful with what we have right now, whether it's a simulation or a small quantum computer? And two, what can we do when the computers come? Right. So a lot of the research is what can we do when we have computers this big, the Shor's algorithm, like the base cryptography, things like that. But our work was in what can you do in machine learning. And so Amir, for example, has done a lot of neural networks, like supervised machine learning, right? Like they built quantum neural networks for supervised learning, and they've got some great results. We were focusing on unsupervised, and the reason is I kind of look at, I mean, in my head, a quantum computer is a generator, whether you want it or not. And a classical computer is more of a supervised learning machine. So for me, because let's think of the most basic generative machine learning problem. Let's think of the most basic generator in existence. It would be flipping a coin, right? Generating a random bit is the most basic generative machine learning problem. And a classical computer cannot do that. It cannot generate a random bit. It cannot flip a coin. It can pretend to flip a coin and give you pseudo random numbers, but they're not random at all. They're predetermined because everything a classical computer does is predetermined. It's deterministic, which is good for supervised learning because you need a lot of operations to work, you know. But in generative machine learning, if you look at classical generative algorithms, which are very good, like GANs or RBMs or even transformers, LLMs, they always have a random part. Like there's always a part where you pick a random number and you plug it to the network, or you do something like that. You pick out of a distribution, and those things are imperfect for classical computers. So we started noticing that, or we started experimenting with quantum circuit and just measuring it, because the flipping coin problem, which cannot be done on a classical computer, is a 101 for quantum computers. The first thing you learn in quantum computing is, for a circuit, how to measure one qubit. And measuring one qubit is exactly flipping a coin, and there's true randomness. So we were just kind of like making that more complicated, having like bigger quantum circuits, trying to train them in the exact same way that you train a neural network, by flipping the angles a little bit, by changing the parameters a little bit, in order to generate stuff that comes from a data set. And we were getting some results that showed that they were a little better. We were getting some results that showed that they kind of looked farther. You can use things like quantum entanglement to make them look in places where a classical computer just kind of stays within its lane. Like it kind of looks things that are close, but the quantum computer started looking far away and finding patterns that the classical one didn't. Of course, these are all empiric results, and we were doing it for comparing a very small quantum, a very small classical algorithm. But we got some promising results, and I found it very exciting.
That is very cool. So
Yeah.
there's potentially opportunities in quantum machine learning where that true randomness can be leveraged to create some kind of efficiencies.
That's what we thought. So yeah, that's
Nice, nice, nice.